Okay, guys. So today, we're in lecture 4. So we're going to deal with some more analog stuff, op amps, looking at filters too. So, quick review over the last couple of lectures. So recall in lecture 2, we looked at the voltage transfer characteristic right here, where the slope of this is the gain, and here's the offset value, is here. And the typical op amp can be modeled like this, where this A right here is open circuit voltage gain. That's the voltage when the RL is not there. Okay, the RL being there changes, this, they have an effect in those kind of things. The differential input voltage right there, amplifier resistance, amplifier output resistance. You look at the differential op amp and the ideal op amp, and also the percent total harmonic distortion. For lecture 3, we went over a few types of operational amplifiers. The transimpedance amplifier, which converts a current to a voltage. Inverting amplifier here, non-inverting amplifier, unity gain buffer, summing amplifier, digital to analog converter, and difference amplifier. So in this lecture, we're going to cover more on your frequency-dependent feedback. We're going to look at Bode plots. Also examine the low-pass amplifier, high-pass, band-pass, active, low-pass, active, high-pass. These right here are going to be passive, and these are going to be active. So these involve op amps, and these just involve resistors and capacitors. Okay, so frequency-dependent feedback sort of looks like this. So what we're going to do is looking at this, the input impedance and feedback impedance. And remember before, when we looked at the inverting amplifier, these two were resistances. Now we're just going to look at those as being impedances. Because we're going to put capacitor there, capacitor here for these filters that we're going to examine today. And just to remind you, here are the values for impedances for the common components. So for so if you just have a resistor, the impedance is just R. If you have a capacitor, then it's 1 over SC. If you have an inductor, it's 1 over SL. And S, if you remember from 2120, is a complex frequency right here. Now, since we're dealing with phasors, we're going to take this sigma as being 0. That's the case if it's steady state. If it's not steady state, if it's transient, then sigma is not going to be 0. Okay, but for a transient, that's going to be 0. And so you're going to say your S complex frequency is just going to be j omega, and j is square root of -1. Okay, so here's a Bode plot. Okay, so these Bode diagrams, they plot the magnitude and phase of the transfer function versus frequency. Okay, so you take your gain, your transfer function, output over input, and you can decompose it into a magnitude and a phase angle. And that's the same thing as like saying something like this, saying you have some complex number here, and it just equals the magnitude of that number, e to the negative j omega. Phi. Okay, and that corresponds to complex plane where this is the real axis, here's the imaginary axis, and your phasor is like born on this axis, and then it rotates up to some angle phi right here, and here's your new point. So this point right here, that point is A, which is A e to the that shouldn't be negative. Sometimes it is negative, but no, it's J B. And that's how that's plotted out. Okay, complex numbers. Okay, and this right here, the length of that is magnitude of A. That's the angle. Okay. And also, if you remember, this right here is, if you want to put it like in terms of sine and cosine, right? It's cosine phi plus j sine phi, right? And that's the same thing as saying, like you have this real number plus, some imaginary right here. And this phi here is, inverse tangent of the imaginary part over the real part. Okay, that's how you determine phi. So it's just if this is like the real part, that's the imaginary part, you just stick it there, and the ratio that's going to be your phi. So here's an example. Here's magnitude on this axis, and it's typically plotted in terms of decibels. And this log right here, this is your frequency axis right here. Okay? And remember on these frequency diagrams right here, you never get to zero like you typically do. Like if this is time or something like that, or x, if you typically get to zero, all that happens is just you get smaller and smaller and smaller, right? So this right here is 10 to power of 0, right? So that's going to be 1. 10, 1, 10, 2, so it's 100, here's 1,000. Well, this right here is 0.1. If you went further, 0.01, go further, 0.001, it just keeps on getting smaller and smaller. It never gets to 0, okay? So that's the x-axis right here. If you're doing phase, these are angles right here, and that's magnitude, and we'll look at both of those. So this part right here is being plotted on this one. This phase right here is being plotted on that one. Okay. So let's look at a low pass filter. So low pass amplifiers pass low frequencies below the high cutoff, omega h, or equivalently filter out frequency above the high cutoff. Okay. Magnitudes that are attenuated by at most 1 over square root of 2, which is 3 decibels. We found that out at like on lecture 1 or 2. Of the maximum are filtered out. So that's what they mean by filtered out. Okay, so it's not really filtered out. I mean, it's, you want to put that in quotes. It's not really gone. It's just attenuated. Okay, so for example, if you're looking at magnitude right here, and if this is the maximum value of whatever it is, something like this is maybe, is your amplitude as a function of frequency. If you go 3 decibels down from that, so whatever this is some value x, and here's like, x minus, 3 decibels. Anything below that, all this right here is considered to be filtered out. And that's what that means. It's not, it's there. It's just attenuated below that value of 3 decibels, which is 1 over square root of 2 of the magnitude of the amplitude. And the reason why it's square root of 2 is because typically it's really in terms of power, okay? And so power is when you take a signal and you square it. Well, if you square 1 over square root of 2, it's 1/2. So if you go down, if this is the amplitude, like in terms of voltage or current, you go down 3 decibels, that's the same thing as going down power of 1/2 in power. Okay, so that's why. So if the power that comes out is half of the maximum, then it's called being filtered out. All right, so that's what that's all about. So the bandwidth of a low-pass filter is basically this frequency right here, the cutoff frequency, minus where you're going all the way to 0 frequency, which is DC, so just omega h. So here's the form of the most simple low-pass type of filter. It looks like this. And so we'll look at this lecture a few times, and we'll get the gain, and then you try to put it into this form, okay? Where this part right here is the gain of the maximum value, and you want to get it to be, the denominator to look something like this, okay? That allows you to plot it out quite easily. And then once it's in this form, you're able to pick off, just by inspection, what that cutoff frequency is, omega h, okay? And here's the block symbol for a low-pass filter. And I guess the way you want to look at this is, here's some sinusoids coming in. Here's the high frequency sinusoid. Maybe that's a low frequency, that's a mid band frequency. So these are crossed out, and so only the low frequency goes through. So that's what it looks like. Okay, so so taking from this part right here, and we'll take a look at this. We examined some systems, but just taking a look at this, here's how you get the magnitude plot. Okay, so what you're doing is you're like starting from here, you're replacing the S with j omega, right? And then you take the magnitude of the whole thing, okay? And remember, if you have like a real and imaginary part, if you have, let's call it A plus JB. The magnitude of that is the square root of A squared plus B squared. Okay, that's where that, just to remind you guys what that's all about. That's where this comes from, okay? And then you factor out of there the omega H from top and bottom, and you have it look like that. And so once it's in this form, then you can take convert this into decibels. And remember, when you're doing logs, the log of like, I don't know, C over D is the same thing as saying log C minus log D. Okay? So that's where this comes from, right here. You have two pieces. You have 20 log of the numerator minus 20 log of the denominator. We're using this part right here. Okay. And then from this part, you want to look at the asymptotic values to try to estimate your plot, because you're going to plot by hand on a decibel versus log plot for these amplitude and frequency. So taking a look at this, you want to see what happens when your frequency is really, really small, like goes to 0. Okay, so when that happens, you could put into this equation right here. So when this frequency goes to 0, the denominator becomes like a 1. So here's your amplitude. So at very low frequencies, it looks like this. Okay, or like that, put it in terms of log. When omega gets very large, much higher than a cutoff, I guess what you can do is look at it like here. So when this is very large, well, just look at the denominator. When that piece gets very large, this becomes insignificant. So your denominator is basically like square root of just omega h squared, which is just omega h. So, yeah, so when this gets very large, I'm sorry, not this part, this part. When this part gets very large, this gets insignificant. Yeah, sorry about that. This omega h is a constant. This is your thing that's changing. So this dominates, that becomes insignificant, so your denominator just becomes omega, and the numerator stays the same. Okay, and you can describe it like this right here. Okay, and for the case where omega equals omega h, when omega right here equals omega h, these two combine, and so you have 2 omega h squared in the denominator. They cancel, and that's where you get the square root of 2 out of it. Okay, or you can describe it like this, where it's the numerator minus the denominator. So 20 log of 1 over square root of 2 is your minus 3 decibels. So that's why you're getting your cutoff frequency, which I just described earlier. Here's the reason why, is because it's your maximum value that you're going to get from your gain minus 3 decibels. Okay? That's what determines cutoff. So it looks like this. Okay? Here's your omega h, right here. That's the cutoff. Remember, it goes all the way to 0 frequency, right here, and just goes like this, and then it sort of, I mean, you plot it like this when you do it with your pencil, but the actual curvature. I mean, it actually curves right there. It's not like really a sharp reflection point right there. Okay. So, so for the low right here, you're going to do your 20 log A. That's this line. For your high regions, you're going to plot it like this, where it's that 20 log A, that constant, and then it drops off at this kind of rate right here. That's where you get the slope right here, which is negative 20 decibels per decade. So it means that every decade, every time you go by an order of magnitude, factor of 10, it drops by 20 decibels because of that right there. So that's like a slope. Okay. And here's cutoff, right here. So that means this point right here, if you went over here, that would be, 3 decibels below this. Okay. So any questions about this plot right here? Okay, cool. All right, so the gain bandwidth product. Okay, so G bandwidth, gain bandwidth. So it is the low frequency gain, which was at A, multiplied by the bandwidth. And it's basically a figure of merit for comparing different amplifiers together. Okay, so A, your amplitude, your gain times your cutoff frequency. There's another value, so omega t, which is called the unity gain frequency. And this is the frequency, so remember this came from the magnitude. And the question is what frequency makes your magnitude, magnitude 1? And that's your unity gain frequency, just for terminology. Now I blocked this in, which is the, what this value is right here. Symbolically what it is. Your phase response right here. So for your phase, you just look at the angle of this, which can be described like this. It's in this form. Remember, this is the S over omega H. Okay? And you can describe it like this angle minus that angle right here. And this piece right here is just your imaginary over real. And your imaginary part is this piece. The real part is 1. So that's what that is. And so if you were to plot this angle as a function of frequency, it would look like this. And a few things to notice about this is that when A is real and positive, the phase is 0. Okay? When A is real and negative, the phase is 180 degrees. So, there you go. That's the case where, so remember where we looked at the op amp, looked at the inverting and non-inverting op amp, and we were saying that, well, if your gain had like a negative value and it's real, then it's really 180 degrees out of phase. That's where that comes from. Okay. At the cutoff frequency, the gain, the phase is 45 degrees. So here's the cutoff frequency, because here it's normalized. So it's whatever the frequency is divided by cutoff. So 1 is the cutoff frequency here, and that is at 45 for the phase. So 1 decade below the cutoff, the phase is, it gets closer and closer to 0, right? So here's the phase, 1 decade below it, you're right here. That's that cutoff, and it's like a 5.7. And 1 decade above it, you're up here, and that's like 84.3. If you go 2 decades, 1, 2, then you're looking at 89.4. So it's getting closer and closer to 90, which it asymptotes to. And then 2 decades below this, right here, 1, 2, it gets to always at like 0.06. So getting closer and closer to 0. Another thing I want to remind you guys. So when you're looking at this right here, this value right here is 1. Remember, it doesn't go to 0. Okay. This value right here is 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, I'm sorry, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, 400, 500, 600, 1,000, okay? So that's how it goes. All right, so let me ask you, if that line right here is 0.01, what's that point right there?
0.02.
Yeah, 0.02, 0.03, 0.04, all the way to get to 1. I mean, 0.1. Good. Okay, so that's how to read those horizontal. So here goes low pass filter, for example. And we're going to use this property right here. So remember, if you have like two resistors or impedances in parallel, you can use this right here for the overall impedance going from the top to the bottom. So these two multiplied, divided by those two things added together. Okay, so that's what we're going to do here. So we're going to look at the gain here. So let's try to find out what this is, and that is, well, we already know what that is. Then we'll take the ratio of those. Okay, so this is like current division. We can, the voltage division. So we can use that here. So combining these two together, okay, so that's like R2 at 1 over SC, the impedance of this, those two in parallel, right, divided by the sum of everything. So this, the impedance of that, and the impedance of this. So the impedance of that and the whole impedance of that, okay? And then using our condition here, we just, expand it all out. And then once we have that, we divide these two together and just get the this type of relationship. This some reduction is done here, but the key here is to get it into that form we were talking about for plotting it out. Okay, so this piece right here is like your A0, your gain, and you want it in this form right here so you can easily plot those things out, and also determine what your cutoff frequency is once it's in that form. So, like for example, if you plug this into here, then you'd find, it don't make sense to you how it was reduced to that point. So that's how you find that. Okay, high pass filter. So, so high pass amplifiers pass high frequencies above the low cutoff omega L, or equivalently filter out frequencies below the low cutoff omega L. Magnitudes that are attenuated by at most, well, same thing as last time, right? Still that 3 decibel down is where the cutoff is. And here's the bandwidth, a little different. So it goes off to infinity, and then you have this low frequency cutoff point right here. So the bandwidth of a high pass filter is infinity. Here's the simplest single pole high pass filter. It has this kind of form right here. Notice the difference. You have this, S instead of omega in the numerator. And so it looks like this. And remember, this is the low pass one, just to compare. And you see the differences here, where you have that inversion of those two things. Okay. So here's a symbol for it. So the highest frequency goes through, the mid-band and low frequency, you're crossed out. That's what the block diagram thing looks like. Okay, so we're going to do magnitude and phase type of plots. For the magnitude, we get this right here. And again, for the low, for the high frequencies, for omega, like really, really high, you just, plug it in here and see, what you get. So if I were to plug this, a high frequency in for here and here, this would become insignificant. So the bottom would be square root of omega squared, which is just omega. So they would cancel out, and I just get A. If this was low, what I would want to do is, yeah, that was low. Okay, so yeah, I know omega is there, but we're looking at that one because these two are being added together. And if that is really small, this is going to dominate, so it's almost like that's not even there. So the denominator is going to be just omega L over some small value of omega. So that's where you get this from, right here. Okay, and then for cutoff, you just make your omega be equal to omega L in there, and then you get this again right here. And remember, 1 over square root of 2 is really -3 decibels, and this is what we get. Okay, so you have a positive slope right here, 20 decibels for every decade is the slope of that line. The bandwidth starts here, but it just keeps on going because all these frequencies, really high frequencies, keep through. Okay, so here is an example. So instead of having this capacitance, this capacitor in parallel with the load here, we're going to put it like this, so everything's in series. And the voltage right here is just this resistance divided by all these added together, which is what we get at the bottom in terms of impedance. And remember, we're steady state, of course. So taking the ratio of that and putting it into the right form, you put it into this form, and then whatever you have here is your cutoff frequency. Okay. So a bandpass filter. Okay, so very similar to what we've seen before. The differences here are that looking at the bandwidth, it just goes from the omega H to omega L. So you have this middle, this mid band you're trying to get through. To get the transfer function, you can multiply the high pass and low pass that we've seen before together, and you get this kind of form right here. And here's what the block looks like, where the middle frequency gets through, the high crossed out, low crossed out. Okay, so here's the Mantoux response, right here. And here's the phase response, looks like that. Okay, and here's the low cutoff frequency, high cutoff frequency, and this, the point where it crosses is 3 decibels down from wherever the high is. Here's like 20 decibels per decade, negative 20 decibels per decade. And again, this is for a first order type of filter. Later on, we'll look at higher order filters, but for every order, it's going to be a factor of 20 decibels per decade. So, for example, if it was a second order system, then you would be 40 decibels per decade. Third order system would be 60 decibels per decade, and so on. Here's a high Q bandpass filter. Okay. So the Q is generally defined as your resonant frequency divided by your bandwidth, omega H minus omega L. Okay, and your bandwidth is defined as the point where 3 decibels down crosses, right? So wherever your height is, it's at 10. 3 decibels down from that is like around 7. Okay, so here would be your omega H, and this point right here would be your omega L, and that would be your bandwidth of that. Here's what it looks like, where this is the Q, the quality factor. So if your quality factor is really large, your bandwidth is going to be very narrow for that, or you have a very high resonant frequency. Okay, and here's also the phase for a high Q type of filter. For a band rejection filter, looks like this right here. It's also called a notch filter. Here's the transfer function. Here's the phase. You're here to plot those out. And what this looks like is your middle frequency is cut out, and just your high and your low frequencies pass through over here. The low frequencies pass through here. High frequencies are able to get through over here. So let's move on to active filters. So, so here's the basic building block for an active type of system. Okay, and if you recognize it, it's just your inverting amplifier. right? And so we know what that looks like. It's a negative, and that was our feedback over R1. Will be just our feedback over R1 times your input voltage. But in this case, it's your impedances. So it's the same form, okay? And that's for sinusoidal steady state. So let's look at this case right here. Here we're going to take your impedance for feedback. We're going to put that in terms of a resistor and capacitor in parallel. And we'll see that that looks like an integrator too. But for now, let's look in terms of this frequency for a filter. Let's look at this in terms of our filter. So for Z1, we have our R1. For the feedback impedance, we have this in parallel with that. So we have this numerator where this is in parallel with this one. So we have this times that over that plus that, which we can reduce to this form right here. And so if we want to look at your gain, it's just this over that, your impedance of your feedback over Z1. And so we plug these two guys in right over here. We get this and that. And then what we can do is divide the top and the bottom of this fraction by RF. You get this. Okay? And then what we can do is sort of like put this on the denominator, right? So we can get into this form, and then we find out by looking at that form where the cutoff frequency is. So it's just 1 over this right here. And then this factor in front of that, that's your 0. So this is what it looks like right here. So your low frequencies are going to go through, and your high frequencies are attenuated at negative 20 decibels per decade. So I wrote this here too. So okay. So this line is like a a linear type of equation. At least as part of it. So you can look at it as y equals mx plus b, where this right here is the slope. That 20 right here just happens to be the slope. Well, it should be negative 20, but okay, that's the slope. And then you have some b-intercept that happens somewhere, but that's what that component looks like. It looks like a very straight line when you can plot it. Now this is for an active low-pass filter. So in this case, instead of having the capacitor in parallel with the resistor, you put your capacitor right here. Okay. And so for Z1, we have this situation, which is this plus that. They're in series. And for your feedback, just RF. And then taking the ratio again, you can see how we're working this through to get it into this form right here. And then once it's in that form, then we can pick off what omega L is. So in this case, it's 1 over C1 R1, and A is RF over R1. And this A right here is just this right here. Okay, so here's your A0 right there, and then this right here becomes your 20 decibels per decade for your slope. Okay. So any questions? Yes.
Isn't that high pass filter, not low pass?
Yeah. Oh, that's a typo there. I didn't change it. Yeah, thank you. That's high pass. I'll change it in notes. Put it up there. Anything else? Okay, so yeah, we finished quite early. So I don't want to cover too much, and that's all the pages that we have to cover. Do you guys have any questions about the homework? I can answer some questions for homework. Yes?
When there are some harmonic distortions, what is the gain?
Huh?
What is the gain if there is some distortion in the...
Oh, what's the gain if there's some distortion?
Yeah.
Oh, are you talking about like the total harmonic distortion? Okay, yeah. So when you're looking at total harmonic distortion, So we have something like, VDC, then we have this, maybe like your first one, then you have like some sinusoid, right? So say cosine, omega t. Then you have some other higher harmonics. And so on. So the gain you want to look at is this one, because that's the one you're most interested in. These are like other voltages, but and they may be quite large, right? But you're not really interested in those. So when you're looking at the gain, it's going to be your output one you're looking at divided by whatever your input one was. So it's just this one right there. And you really don't look at this too much. I mean, it depends what type of analysis you're doing. Your DC can be amplified, okay, going through an amplifier, but you're really concerned about your signal. So you're really concerned about, what happens to my signal? Like how much is that amplified? And so it's really this one where you're looking at the fundamental harmonic. Okay. Yeah. And let me write in here what maybe the input would have been. So, for example, let's say your in was like, it was like 2 plus, 5 cosine 60 pi t, right? Your output that you get out is going to be something like, it could be like 100 here, but this part here could just be like maybe 15, right, for V1. You're going to still have that same frequency here, 60 pi t, but you're going to have some other distortion. So you may have like maybe 0.1 sine, that's be 260 t. You may have 30 sine 360 t pi t, and so on. But the thing you're looking at is this piece over that piece for your gain. Yeah, so in that case, your gain would be 3. Yeah, so that's a good question. What else? Yes.
So there's one that's asking about the out, and it gives you an input sinusoidal waveform as well as a DC offset. And I'm not entirely sure how to do that one.
Pretty sure the answer is wrong.
Yeah.
It should be.
The correct answer is given as a DC voltage, whereas it's not hooked. It's not hooked.
Okay, and what was that again? It was
question
Here, I'll
2.5.
show you.
Okay.
It's telling me that the answer is 1. This number 5.
Okay, so DC is.
And I would think it would be A, but I'm not specific on that.
Oh, okay, so. Yeah, so. It's kind of funny. So on this one, so this, on 2.5, so your DC, your VDC, it looks just like the picture, right? So that's going to be 1. And then it's asking for the output. So then you just like carry it through. You could do it in the form of a picture. Well, in this case, you have to do it that way. So you're saying it doesn't match up with one of the answers?
Yeah, so it's telling you that the answer is 1. Or D.
Oh, you mean A?
It's telling you the answer is answer E.
Oh.
A is wrong.
Oh, yeah, that's not right. Yeah, that's not right.
Okay, so the answer should be A.
Wait a minute. So in the selection,
The correct here. In that tab, you can see that the correct answer answer 7 is easy on the spot.
Oh, wow, yeah, that is wrong.
Yeah.
that is way wrong.
That was my conservative.
Yeah. Okay, yeah, so for this one, yeah, I'll draw it up here.
Alright.
Okay, so. Okay, so it looks sort of like this. Well, I forgot what it looks like, but so it looks sort of like this, right? And then you have some sinusoid right here going through there. And so graphically, you're just taking that and you're just matching things up. You know, whatever that happens to be. And then this is where you're getting your DC for your output, right? And then your amplitude right here, whatever that is. And then you can make your sinusoid after that. You know, it'll be your VO, DC, plus whatever A is, sine, omega t. So, you know, something like that. And you're saying the answer is A? Yeah, okay.
The correct answer that you just gave would be A, but it says E 1 volt is the correct answer.
Okay. He's testing you guys. Yes.
On the last homework, number 6 is determining G parameters. Could you go through maybe 1 or 2 of those G parameters? Work on that for us?
Okay, so let's see here. Did you have it like this showing what it is? I give you last time. Okay. Okay, so the problem with something like this, and it concerns the G parameters. So let's put back on our little thing for G parameters. Hold on a second. Okay, so for our G parameters right here, we have this thing right here that we have to go by, right? So for example, if you're going to look for G11, you're looking at the ratio of this current and this voltage right here, the ratio of that, and you're letting this part right here be 0, right here. So this, you're leaving this as like an open circuit, right? And you're looking at the ratio of those two things right there. So what you typically do is you apply a voltage right here, okay? And then you do your circuit where this part is like an open circuit. So there's no current going through here, okay? And then you do your analysis. You know, for example, you know, you'll say something like this, where here's your V1, right? And then you just do your circuit analysis. Now, of course, this right here has a current source and a resistor. So when you do your KCL right here, you're going to have this, from this node, this is going to be V2, right? So you're going to have, and let's say this part down here is ground. So you're going to have V2 minus 0 over 220K. That takes care of that current. This current right here is going into it, so it's minus 150I1. And this current going out that way is going to be, you could think of it as like either negative I1 equals 0, or you could think of it like this. You could say this. You could say it's V2 minus V1 over 10K. And then you have another equation that says negative I1, or just I1, equals V1 minus V2 over this 10K. Okay? And these two equations right here, you have your V2s. And so you solve this for V2, you plug it in here, and then you have an equation in terms of I1 and V1. And then you just manipulate it to have the ratio of your I1 and V1, and that'll give you your G11. You guys see that? Yeah. Does anyone not see that? Is that helpful? And it's the same with all the other ones. Okay, so like for this one right here, your V1 is 0. Okay? So so for V1 to be 0, what do you do to make V1 0? Yes, you shorten it. So you put a physical wire right here, right? And on this side, what do? You apply, either, you can apply a current, you can apply a voltage, whatever you want, you apply something there, and then you find out what this ratio is. And the same with this. For that to be, for I2 to be 0, well, this case, same thing as last time, but then you look at the ratio of that. For this, same thing here, just look at the ratio of those two things. Okay? Anything else? All right, great. I'll see you guys on Wednesday.